The next method for finding the concentrations is integrated rate law. You will find the concentrations at any time. And you will work with concentrations at any time. You are not limited to initial concentrations like the initial rate method. So we will study the integrated rate law for these three orders of the reactions, 0, 1, and 2. The rate law and integrated rate law will be given in the exam, so we don't have to be worried about having this. You have this table in the exam. And here are the integrated rate law. You just need to know how to use them. For the zeroth order, AT is the concentration of component A or reactant A at any time in the reaction, and A0 is the initial concentrations. For first order, you have ln, natural logarithm of A over A at any time T over A0 at initial concentration, which is equal to minus KT. And for second order, you have inverse of AT at any time is KT plus 1 over A0. So let's work on a question to see how we use these equations for working on our problems. We are working on slide number 54 of chapter 13. Cyclopropane is used as an anesthetic. This isomerization, the isomerization of cyclopropane to propene is the first order reaction with a rate constant of 9.2 per second. So K is 9.2 per second. Okay. If an initial sample of cyclopropane has a concentration of 6 molar, so let's just call cyclopropane A. We are not going to write or draw the molecule. So cyclopropane, let's assume is A. Its initial concentration is 6 molar. And what will the cyclopropane concentration be after 1 second? So we are looking for concentration after a while, and that time is how many seconds? Just 1 second. Okay, so we know that for a first order reaction, the rate is this, and the integrated rate law, because we are looking for AT, is written as ln of AT over A0 equal to minus KT. So ln of our unknown divided by 6 is minus 9.2 per second times 1 second. So look back here. So ln of AT over 6 is minus 9.2. And then in order to, the opposite function of ln, in order to cancel ln, is e. So a t over 6 is equal to a to negative 9.2. And at the end, you will find AT is 6.1 times 10 to negative 4 molar. So that's how you apply these equations to your calculations. Another piece of information which is given to you to work on these types of problems is the half-life. Or allow me to write half-life here because I want to talk about these equations. Half-life. Half-life for a zeroth order reaction is initial concentration of A over 2K. For first order reaction is 0.693 over K, and for second order is 1 over K times initial concentration of A. We left this column. Why? Because if a diagram is given to you and you're supposed to find the order of reaction from that diagram, let's find out which one, what is the components of this diagram. They are all in the form of a linear equation. So y is mx plus b. Here a versus t, and what would be the slope? Minus k, right? And this example, ln a t versus t. Just say ln. And again, slope is minus k. And here, ln of, 1 over versus t. And this is the only positive slope, right? So if you are dealing with a positive slope, if you have 1 over at versus t, and you have a positive slope, you have a second order reaction. So let's work on one example. I will leave the table. Okay. This reaction is given NH4 plus NO2 negative gives N2 plus 2H2. In a solution that is 10 molar in NH4, the reaction is first order. And the rate constant at 25 degrees Celsius is times 10 to the third per second. What is the half-life? Half-life is shown in T half. and I'm working on slide 59. So in order to find the half-life, we are talking about the first order. What is the half-life of a first order reaction? This equation, T of half-life is 0.693 over K, which is 0.693 over, what was K? 3 times 10 to the third per second. So half-life will be 2.3 times 10 to the second. And if you need to change it to a minute, then go ahead and divide it by 60. So it's going to give you about 4 minutes, 3.9. That's how you apply these types of equations. So now let's work on slide 65. Slide 65. Let's see what the question is saying. It's a concept check. A reaction believed to be either first order or second order, and it has a half-life of 20 seconds at the beginning of the reaction, but a half-life of 40 seconds sometime later. At the beginning of the reaction, half-life is 20 seconds, but half-life changes to 40 seconds. What is the order of the reaction? So let's write down the equations for zeroth order, first order, and second order again. For zeroth order, it's initial concentration of A over 2K. For first order is 0.693 over K, and for a second order it's the initial concentration, we know that over time decreases, right? So the initial concentration decreases, but your half-life increases, right? If the initial concentration decreases, so this zeroth order is not showing the increase, it's showing the decrease. So but we are looking for a concentration in which it is increasing, the half-life is increasing. For the first order, it doesn't change with the concentration, but here, by decreasing the concentration, the half-life increases. So you can conclude from the equation for half-life that this is a second order. Alright, after knowing all these, we can talk about the rate constant and their relation to the temperature. It takes us to the collision theory and activation energy. The theory is that the temperature increases the reaction rate, and also because the collisions are going to be more, also the collisions should be in the right direction. So the collision between the molecules in a reaction should be with proper energy and proper directions or orientation. So it is believed that the reaction starts from reactants. It takes it to an activated complex, which is a sort of transition state. We call it transition state theory. It's a transition between the reactants and the products. So it is believed that the theory says that the reactants first change to an activated complex, which is a transition state, and then they change to the products. The example is NO plus Cl2, which gives NoCl2. The symbol for an activated complex is something like a pound sign, but with a straight line. And then it changes to NO and NoCl, NoCl and Cl. So this is your activated complex. And for the reaction, reaching to this activated complex is the difficulty of the reaction. For example, if you draw the energy diagram for energy versus reaction proceeding, you will have the reactants here. Let's say you have NO and Cl2 here. Then these NO and Cl2 need to form the activated complex, which has a pretty large energy barrier. This is NoCl2. And then they will form the products, NoCl plus Cl. What you need to know at this point is how to read these types of diagrams. The distance between energy level of reactants and activated complex is called activation energy. Activation energy. And the distance between energy level of products and reactants is the delta H, or heat of reaction. Delta H, or heat of reaction. If reaction goes backwards from products towards the reactant, then NoCl and Cl are going to be your reactants. So this amount will be the activation energy for the backwards reaction. This is for forward, I call it F, and this I'll call it B, activation energy of backwards. And you should be able to calculate the numbers. So if the activation energy is given to you on slide number 74, if the activation energy here is 85 kilocalories, kilojoules, I'm sorry, kilojoules per mole. And if delta H is 83 kilojoules per mole, can we calculate the activation energy for the backward reaction? Definitely. For the reverse reaction, it's this distance minus this distance, so 85 minus 83, which is only 2 kilojoules per. So reading this type of energy diagram is important for us. You have a similar example on slide number 77. On slide number 77, it says, this is the reaction N2NO. All of them in the gaseous form. The activation energy for the forward reaction, activation energy for forward reaction is 251 kilojoules, and delta H, the heat of this reaction is 167 kilojoules. Label your diagram and sketch this potential energy diagram and label it and determine the reverse activation energy. So, first, from CHEM-1 we know when delta H of a reaction is positive, it's endothermic reaction. The reaction has absorbed heat, so the level of products is higher than that of the reactants. So we are safe to say something like this happened. N2O, activated complex, we don't know what it is, and the products. Activation energy is given as 251 kilojoules. Activation energy is the distance between reactants and activated complex. So activation energy for the forward reaction is 251 kilojoules. Also, delta H is given. Delta H is 167. Delta H is the distance between reactants and products. So this delta H is 167 kilojoules. And the last thing is asked in the question is to determine the activation energy of reverse. Which one is the activation energy of reverse? In the reverse, products become the reactants. So the difference between the products and activated complex, it would be the activation energy of reverse, which would be 251 minus 167. And if you subtract them from each other, you will have this activation energy as A4 kilojoules. Then in two different temperatures, because the temperature is going to affect the rate and the rate constant. So we deal with Arrhenius equation. Ln of K2 over K1 is activation energy over R. This will be given in the exam. This is how we calculate the activation energy or the rate constant. So it takes us to slide 81. In a series of experiments on the decomposition of dinitrogen pentoxide, rate constants were determined at two different temperatures. At 35 degrees Celsius, you see in the Arrhenius equation the temperatures are given in Kelvin. So go ahead and add them to 273 right away. It would be 308 Kelvin. And what else do we have? We have rate constant here. K1 is, that was T1. K1 is 1.4 times 10 to negative 4 per second. T2 is 45 degrees Celsius. We add it to 273, which is 318 Kelvin. And K2 is 5 times 10 to negative 4 per second. So we are looking for the activation energy and then value of rate constant at 55 degrees Celsius. So let's plug it in to the Arrhenius equation. We have it, Ln of K2 is 5 times 10 to negative 4 divided by 1.4 times 10 to the negative 4, both of them per second. So let's get rid of 10 to negative 4, 10 to negative 4, since they're the same. EA is unknown, you're solving for it. And be careful, you're dealing with energy and the unit in joule. So the value of R is 8.314 joule per mole Kelvin. Then T1 is 1 over 308, 1 over T1 minus 1 over 318. And when you do your calculations, you will have you calculate this. I mean 5 divided by 1.4, ln of 5 over 1.4, EA over 8.314, and put them in your calculator. And then in order to get rid of ln, you take them to, E over e to the power of that number. So E will be 1 times 10 to the 5th joule per mole. In the second part, when you need to find K or activation energy, let me see what it said. The value of rate constant at 55 degrees Celsius, then you will use any of these temperatures with 55 degrees Celsius. And K2 is for that. I'm not gonna go over it. You know how to do it. I don't want this video to be too long. All right, the next concept is the reaction mechanism. When you talk about the reaction mechanism, means talking about the details of a reaction, which happens in different steps. Different steps of each reaction. Are called elementary reactions. So the summation or the total of elementary reactions is called the reaction mechanism. In the reaction mechanism, there is always one step which is the slowest. That's the step that takes the reactants to the activated complex. And because the activation energy is high, so that would be the slowest step. Slowest elementary reaction or slowest step in a mechanism is called rate determining step, or we just call it RDS. So let's work on slide number 92, see how we can determine what we just talked about. We have a reaction with these two steps. So it says this first step is the slow step and the second one is the fast step. So you call the slow step rate determining step. And you write the rate law from rate determining step. So what is the rate determining step here? This reaction. So how do you write the rate law? We said we use K, reaction constant, and then NO2, 1 mole plus 1 mole, so NO2 and F2. That would be the reaction right, or rate law for this equation. When you add, for this reaction, when you add these two and cancel the components that they are the same, you will end up having the final equation. So here we have 2NO2 plus F2. On the other side, you will have 2NO2 F. That's the overall equation for the reaction. There are two things that you need to determine, you need to be able to determine in the reactions. I'm not going to erase this because I need it. One of them is reaction intermediate. Reaction intermediate. Reaction intermediate is the species in the entire on all of the steps that is produced and consumed in the next steps. So I didn't erase these equations, this reaction. Let's determine which one is the reaction intermediate. What you see has been produced and has been consumed in the next step, F, right? So here the reaction intermediate is F. Another thing that you need to be able to determine in the reaction mechanism is the catalyst. You all know what is a catalyst. Catalyst is a species which is not consumed. Okay? So even if it shows that it's consumed in one step, it will be produced in the other step. It's not consumed, you will have it at the end, will remain at the end, and it just decreases activation energy, so speeds up a reaction. So if we go with the energy diagram, and this is the energy diagram without catalyst, then if you use a catalyst, you may have this route. So this is with catalyst. You see that activation energy was this much, EA1, but EA2 is only this amount. So this barrier is going to be lowered down and the reaction will be faster. So like the enzymes in the body. Now let's work on the last question you have on slide 101. You have a couple of questions. You can work on them easily. I'm not going to work on every single slide. Plus O2. This is your RDS or slow step. And the second one is ClO plus O gives Cl plus O2. What is the overall reaction equation? the overall reaction. First, let's get rid of what we don't need. So the overall reaction is O3 plus O gives 2O2. That's the overall reaction. And we are supposed to find if there is any reaction intermediate, what has been created but has been used at the same time. Intermediate between these two, which one has been created in the first equation but has been used in the second equation? Isn't it ClO? And also, do you see any catalyst here? Yes, it looks like Cl has been used in the first equation, but has been produced at the end again. So you will see, sorry, I forgot O here. So catalyst is going to be Cl. So the catalyst and intermediate are the opposite of each other. Work on the questions and each question, and let me know if you need any help with any of them.